Hello, everyone, and welcome to May I AI. In this episode, we explain what reasoning is and we try to figure out how AI does it and if it works exactly the way humans do reasoning. Let's dive right in. Imagine this: you walk to the nearby park. When you get there, you realize that the grass is wet. You look around and you realize there are sprinklers and a fountain. You make the assumption that in order for the grass to have gotten wet, the sprinkler must have turned on or the fountain must have splashed water. You also think maybe it could have rained, but the weather app says that it hasn't rained overnight. You look at the distance between the fountain and the grass and you realize that the fountain is a bit too far away for it to splash all over the grass. So it must have been that the sprinkler was turned on. Was that guesswork? Kind of. It's educated guesswork. It's making guesses based on the most likely option, based on the things that you can see all around you. It includes deduction to look around and deduce what are the options that could have made stuff possible, but also abduction to make sure that you can guess or assume what is the most likely option. In other words, it's reasoning. Reasoning is a skill most humans have trivially. Actually, most humans do it every day. Whenever you're talking to someone, whenever you're listening to me talk right now, you're doing abduction. This is because human language is actually ambiguous, meaning that words have different meanings depending on who's saying them, when they're saying them, and what is the context behind them. So whenever someone says something, your brain does trivial abduction in order to assume what the most likely option is. But if people can do this trivially, can machines do it too? Have machines already figured out how to reason exactly like humans do? Let's do what we always do, go back to the very early beginning and try to see how we can define reasoning before we go forward. The study of reasoning dates back to ancient philosophy, with very early contributions from Greek philosophers such as Plato from 427 BCE. In the late 19th century, up until the early 20th century, the field transitioned from philosophical discourse to experimental psychology. Some would argue that this is where real AI should be. You see, modern AI is actually pushed forward based on necessity. It's driven by what the people need based on what they cannot do. And that includes doing stuff that machines are better at doing than people are. This, for example, includes doing very big calculations or doing protein folds, stuff that people can do but they're just very slow at, where AI can optimize and do it way better. But some believe that the hardest tasks to use AI for aren't the stuff that computers do better than people, isn't the stuff that people cannot do, but rather the things that people do trivially. In this case, like reasoning. In today's world, a lot of research is trying to test whether or not LLMs are able to reason properly. For example, there is towards reasoning with large language model and reasoning with large language model prompting. Both surveys trying to deduce all of the research doing on that area, but also more recent papers that argue that models are not able to reason at all, for example, the illusion of thinking or other papers. However, because of the whole controversy with Apple and the papers that have been coming up and the responses to them, I'm gonna ignore the illusion of thinking entirely for this episode. But before we dive into LLMs and try to see what the research says about them, let's actually look at the formal definition of reasoning and have an idea, a formal idea of where we stand and how we can actually look at something and decide whether or not it reasons or not. Now, there aren't really any universally accepted definition out there, but there are multiple frameworks that have been proposed that are used for this. For example, there is the mental modes theory by Johnson Ladd. It argues that human reasoning isn't the strict process of applying logical rules, but rather the creation of mental modes that cover all possibilities. Basically, how people can build these mental models of all possible information and scenarios and then use that to logically deduce conclusions. Mercier and Sperber argued that the primary functions of reasoning is actually argumentative, meaning that people try to devise and evaluate arguments to convince other people of different things rather than try to find a logical truth value. However, if we look at the most cited definition, we can use this one that was also published by a book in Cambridge that explains that reasoning is the process of inferring logical outcomes by using the three ways of reasoning: induction, deduction, and abduction. Human reasoning is usually defined as the cognitive process of inferring these inferences. AI, or computer based reasoning, on the other hand, is usually defined as the ability of a system to analyze some information and make decision based on learning, pattern matching, or using logic based rules. AI reasoning is usually implemented by one of three options: symbolic reasoning, And this is using logical rules, for example, if X then Y rule based systems, statistical reasoning, which used learned patterns. These are like neural networks and machine learning models of today, and hybrid reasoning, basically a combination of the previous two methods into one bigger system like neurosymbolic AI. Now that we have an idea about the formal definition, we're going to take a look at reasoning through the years, starting from the very early days up until AI reasoning today. We're going to start at the 1670s with the Leibniz calculating machine. It tested the very first mechanization of arithmetic operations and showed that these calculations could be automated, although with very small practical uses. In 1764, Bayesian inference was introduced. It tested the use or application of probability to reasoning under uncertainty. This resulted in the generation of a statistical framework that underpins much of the use of modern AI systems today. In 1854, George Boole tried to see if human logic reasoning can be represented algebraically. This started Boolean algebra, which is the foundation of digital logic as well as computer circuits. In 1950s, Alan Turing introduced the universal machine, which showed that any computable reasoning could be done by a machine. This is also when he proposed the Turing test as a benchmark to test computer intelligence to human thinking. In 1956, Alan Noel developed the logic theorist as a way to test the automated theorem proving, which he successfully was able to prove 38 out of 52 theorems from the Principia Mathematica. This showed that machines could actually do symbolic logic reasoning. 1 year later, Alan also proposed the general problem solver, which tested general problem solving as well as symbolic reasoning. It showed that computers were able to do means-end analysis to solve a variety of computer puzzles. From the 1960s to the 1970s, the researchers at Stanford developed expert systems, which showed that they can encode domain-specific knowledge as rules. This showed very high accuracy in medical diagnosis as well as chemical structure euclidation. In 2010, we got deep learning and AI, which you now know more about. And in 2020, we got neurosymbolic AI, a way to integrate deep learning with symbolic reasoning, which achieved much more accuracy in reasoning tasks. And finally, today we have large language models, which have been tested through various benchmarks on reasoning tasks, showing state-of-the-art accuracy, but still showing large limitation in statistical reasoning. Most AI systems that include reasoning and do really good at their tasks are very domain specific. This is because symbolic reasoning requires the manual creation of rules and logic for specific tasks. As for now, the only general AI systems that can do, let's say, non-domain specific reasoning are foundation models, which for now are large language models and visual language models. So while most of the older models that do really good at their tasks are really good at doing reasoning, they're not the systems that people talk about when they say AI reasoning. For the rest of this episode, I'm going to be talking about large language models, which I assume what most people are wondering about when they ask whether or not AI can do reasoning. Let's look at this paper published in 2024 titled Understanding the Limitations of Mathematical Reasonings with Large Language Models. The authors showed a new benchmark that tested large language models on mathematical benchmarks that showed that LLMs are quite fragile when the problem either changes in format or increases in complexity. They showed that large language models' accuracy on these tasks dropped sharply when they slightly rephrased the question. This shows that large language models usually replicate training patterns rather than reason from scratch. There was another paper also published in 24 titled Large Language Models Are Not Strong Abstract Reasoners. The research tested LLMs on abstract reasoning tasks and showed that they perform poorly, and even fine-tuning and further training the models did not do much to increase the performance on these tasks. They showed that models were not able to grasp the abstract patterns or the causal mechanisms. There was another paper titled The Limitations of Large Language Models for Understanding Language and Cognition. The paper argues that despite the fluency shown by LLMs, they do not show the acquisition of language or depth of reasoning as humans do. This is especially in tasks requiring open-ending interrogative understanding. And finally, a paper published in 2025 titled Large Language Models Still Lack General Reasoning says that all claims about LLM's reasoning are actually premature. They showed that models LLMs still struggle to generalize across multiple tasks when it comes to reasoning skills. Now, while I'm sure there is a lot of papers out there that talks about LLMs doing great on some reasoning benchmark, the question will always be whether these benchmarks are actually new to the model, that the model generalized to knowing them, or they were part of the training in some way or form. Meaning that we cannot really tell if the model is solving the problem as a way of doing pattern matching rather than doing internal logic and reasoning to find the answer to that task. While it's no secret that AI models of today are really good and they excel at statistical reasoning and using their learned data to pattern match and find the best possible outcome and prediction, this is not the same way that humans do reasoning. This is not the reasoning skills that most humans have trivially, and it's not enough to solve most problems that human can solve. Now, I know some of you may have heard of chain of thoughts, and those that did probably think that this means that the models can reason and can show more thinking, let's say. For those of you who haven't heard, chain of thoughts is a way to prompt an LLM model to also show intermediate thinking steps. This allows the model to show better accuracy, but also do a lot more step-by-step problem solving rather than reaching the end of the solution right away. And as you might think, because the model thinks in step-by-steps instead of just randomly giving you the first answer it can come up with, the model does show better accuracy. Actually, a lot of papers have shown that these prompting techniques allow the model to do better and increase the accuracy on a lot of reasoning tasks. But is this actual reasoning? Is this actually the model doing internal thinking? Not really. The truth is that these are still statistical ways of generating an output. The difference here is that, like I said, instead of the model just generating the final answer right away, the model is prompted to make intermediate steps. And while doing these intermediate steps, these outputs, these thinking tokens, are now being part of the context of the model, meaning that the model has more context and more idea of what the problem is, which allows it to do better statistical reasoning because now the pattern matching has more to work with. We can look at this research paper from the Arizona State University, The Chain of Thoughtlessness, that demonstrate that chain of thought prompting only really makes LLMs do better when the tasks that they work on are similar to or are the same to the problems that they have seen during training data. They show that as soon as the problem deviates from the training distribution or increase in difficulty or complexity, the model's accuracy degrades very sharply. Another paper called Chain of Thought Prompting in the Wild is Not Always Faithful shows that these chain of thoughts prompting is not always an explanation of the answer that the model give, but rather a pattern matching to explain something that the model already saw. So rather than the model explaining its internal reasoning steps, it explains the observation of the output that it already has generated, which makes sense because, like I said, these prompting outputs are not really reasoning, but rather still the model generating more text. It's just prompted to generate steps that seems like it's step-by-step guide to the solution. The truth is that models, even with chain of thought prompting and the ability of seeing these thought tokens, are still black boxes. These thought outputs are not really the internal logic of the model, but rather still the statistical best output probability, meaning that we cannot really use these outputs as a way for us to say this is what the model is thinking, which means we really don't have a way to understand why the model generates what it generates. But this sounds more scary than it actually is. A lot of people tell you that we have no idea how models work. And to an extent, this is true, but it's not as scary as people make it sound. This has been a problem with neural networks ever since they were created. We all know how it works. It's complex math. It's a lot of big mathematical equations, but it's just that it's mathematics. The idea is when you have a model that is trained on a certain data and then it predicts an output, we can trace the equation. Of course, the larger the models, the more complex it is to look at the equation. But the problem here is that the parameters that are learned by the model have no explanation to them. And while ways have existed for us to be able to add explainability to models, these usually reflect to which neurons are activated higher to certain inputs and also show, let's say, which of the input features have a higher correlation to the output prediction. But this is not enough for us to explain why the model predicts the output that it predicts, meaning that if the output is wrong, we have no real identification of where in the entire neural network this problem occurs. Now, even if you ask an LLM, why did you generate that answer? it will give you an answer, it will explain something, but these are similar to the very last paper we just explained, are only post hoc plausible explanations based on observations that the model already seen. This is not because the model internally has a way of explaining its own answers, because it's very hard for us to implement this, and the models have no understanding of their own answers, and they have no way of being self-aware to understand what calculations they're making by themselves. Let's, for example, look at a situation where you go to a doctor to get a diagnosis. Now, when the doctor gives you whatever disease that you have as a diagnosis, you're able to ask them why this is the diagnosis they chose. And they will be able to give you a full prognosis of why this makes the most amount of sense. However, if you go to a machine learning model, even if it's a very good model, and you ask it why, the most it can really do is highlight the symptoms that you've showed and says you have these symptoms, and statistically if you have these symptoms you have this disease. But this is not a real explanation. Now, if you ask an LLM, it will also be able to give you this exact response, but in text format. But again, this is just the model being statistically reasoning by generating the most plausible pattern to respond to the answer based on the observation that it has. But it's not really explanation of its internal workings and its internal inference step. And this is why, with today's neural networks and AI models growing larger and larger, AI explainability is a big topic and a big field that a lot more researchers are trying to get into to get models to be more, let's say, open and explainable. So it's clear that the research denotes LLMs and large language models as statistical reasoners, but not really logical ones, meaning that while they show some reasoning as attributed by the definitions, these are more pattern matching based on learned distributions rather than actual logical thinking the ways that humans do. But again, whether you choose to believe that or still think that models do reasoning is up to you to decide. Do let me know what you think about AI reasoning and if you have any remarks on the topic. If you found this interested, share it around so other people can see it too. As always, stay curious, and I'll see you in the next episode.